All right. So how can you apply it? All right. So you're saying H2 prime instead of H prime. You're saying H2 prime, which is fine. Okay, yes, I agree. That's true. So then what will you do with that? I know you got two H's in the middle, yes. Then you'd have x1, x2 is equal, you've got an H sandwich. All right, that's what you got. That's all right. So you're going somewhere, but not where you want to go. Oops. You're going somewhere. Maybe that's not quite what you want. Sorry, I didn't hear, Jocelyn. Yeah, use associative property. What are you going to associate? Well, yeah, but the problem is they're in the middle, and you want them on the right-hand side. So I think you moved the wrong H. How? Well, only if you give me a reason. That only if you say pretty please. I mean, you have to give me a good reason. No, not commutative. Not commutative. No. Not commutative. So this, right? Okay, we're here. Yeah. What? How dare you think you can do something like that? So why couldn't you? Why is that not possible? What do you mean they're not in the same set? Do they have to be? All right, so this one's not working for us. So what you're telling me to do instead, audacious suggestion is you're saying there exists, well, let's call it H prime, such that, and here you're saying that H1G2 equals what? Okay, G2H prime. Okay. So why can't you do that? The answer is there's no reason why you can't do that. You can do that. Why would there be a reason that you can't do it? You can do it. It's the same thing. And in fact, that's exactly what you want to do. Sorry. I guess I don't know. I'm screwing with your mind. So, all right. So that's true. That's true. That's absolutely true. So what are you going to do with that? Oh, yeah, let me do it this way. I'm going to use associative property just to be clear. This is a 2. And that's going to be equal to G1 times G2H prime times H2. And that's equal to, all right, so this is my substitution. Or I guess what I'll say is this is actually, this is associative and substitution. Because I use both properties. So that's equal to G1, G2 times H prime, H2. And that's also associative. All right, so where do I go from here? Yes. So that tells me what? Yes. 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 And I think that's what we wanted. Yes, that's exactly what we wanted. Okay, so you're there. Well, so hopefully this example shows you how you can approach this. You had a good idea here. You had a very good idea here. You just was the wrong one. So you just filled with it a little bit and made it work out. Okay, so Jocelyn, it's your turn. (10.3.17). Oh, okay. Let's see. Did you send me? I thought I answered your email. Did you send me another one? Okay. Well, let me see here. If you want to use Lagrange's theorem, probably that's okay. Let me see. It's just easier to do the other one. But if you want to use Lagrange's theorem, that's okay. Can you share it on your screen? Is it? Oh, you have it on paper. Well, you can send files by Skype. If you go down to the bottom here to the 3 dots and say, whoops, there is a way to send files. I think it's the top right corner. Do something. Yeah, you can do it here in the messenger. Yes. Yeah, sure. Okay. Okay. Say that again. Well, that doesn't sound right. I'd have to look at it, but it doesn't sound right. You can't put a group element in the exponent. The definition of the generator. All right, so here, what we can do is I can write down what you're saying. That's what I'll do. We'll just do that. And let me start a new page. And let me get rid of you here. Goodbye. Okay. All right, so this one is 10.3, what is it? 10.3.17. Okay, and we'll do the screenshot. All right, so you're saying this is what you started out with. You said we'll say let big H be a subgroup of big T, and big H is not equal to E. And then you said so what then? So then there exists a little g in H such that little g is not equal to the identity. All right, and then what did you say after that? Well, you mean the orbit of g, yes. Well, look at the definition. 10.3.16. Here's not k exists in G. This is just k equals. Well, 10.3.16 says that. Well, you said k equals G, and all right, that doesn't make any sense because k is an integer and G is a group element. K is an element of big G? All right, no, that's not true because K is an integer. Actually, what is true is that this is G to the K, and here K equals 1, 2, 3, and so on. However, by proposition 10.3.16, proposition 10.3.16 says that G is a generator of big G. And what that means is this here. What that means that G is equal to big G. That's true. So where can you go from there? Or where did you go next? Okay. So I close your property. What did you say contains H? The orbit of G contains, that's true. Okay, so what does that mean? That's not substitution. That's another theorem that we have. I don't remember what theorem that was, but that's another theorem. 9 something. And that might be after this. I'm not sure. It should be before. I don't see it here. Let's go one more. Maybe afterward. Don't see it here. Let's skip afterward. What is it, Jesse? Oh, 9 by 26. Okay, it's way back there. Okay. All right. So it's so we are good with that. Okay. So where are you going from there? Or equals what? Order big G equals what? Equals H? Equals P. Okay. So what's your conclusion? Okay. Well, all right, so let's stop here for a second. There is a problem here. I'm looking back here. It says, by the closure property, G contains H. So how did that follow? Well, I think you quoted it wrong. I think you quoted the proposition wrong because it's not true. What this is saying is that since you're saying that little g, you're saying little g is in H, is in big H. But by closure, G squared must also be in H, and G cubed, and so on. So it's not true that the orbit of G contains H, but the orbit of G is contained in H. All right. Now, you're going fine so far, and now but after that you're getting off track. So I'm going to erase this. You're almost there. All of this is not necessary, and I'm not sure that you can even use it. All this is not necessary. Well, look at this and look at this. Or let me do it. Let me do it in red. Oops, sorry. How about this? You have this here, and you have this here. Say again? All right, so I can replace this with what? I can replace this with what, according to this guy? Okay. Now, originally, you saw that H is a subgroup of big G, right? So what does that tell me? If H is a subgroup, then this is true. So what do these two things tell me? If I've got, I'm sorry, your connection is not very clear. What did you say again? Yes. Okay. So H was a subgroup of G that was not the identity. And you showed that H equals big H equals big G. So what you have is the only subgroup of big G besides the identity is big G itself. Because you showed as long as H contains something besides the identity, it has to be big G. So what does that tell you about proper subgroups of big G? Since the only subgroups are big G and little e, what does that tell you about proper subgroups of big G? Okay, so that means the only proper subgroup of big G is this. All right, so the key here was that you can do substitution with sets as well as with elements. So that's the key. Okay, so this is on your OneNote. You can look at this also. Jesse, you had one more? Okay. All right. Yes. Short. Because they're all the same set. They're all the same set, so short. You can do that, yes. Okay. So, Jocelyn, let me ask you, when do you get off work? On Mondays. Oh my goodness. All right. I sent you a message that you could call me. I don't know if you got my message.